So the basic criteria to obtain precipitation strengthening, let's talk about that. Okay. Or obtain precipitates. Okay. So what are the criteria to obtain precipitate in a given system, right? So the one of the basic criteria is that the solver's line should decrease with decrease in temperature. Okay, I will explain this using phase diagram. Okay, this also means that decreasing solid solubility as temperature decreases. Okay, so let's understand this with phase diagram. Okay, so let me draw a phase diagram now. Okay, so you have temperature here. Okay, and let's say we have A and B is on the other side, so you are going to have 8% of B, okay, increasing in this direction. Okay, something like this. And somewhere here, say you have beta phase. Okay, and say you have liquid, this is alpha, so this is say alpha plus beta, and then this is also going to be two phase, which is alpha plus liquid. Okay, now which one is the solver's line here? So this is your solver's line. Okay, and see what I wrote before. It says the solver's line should decrease with decrease in temperature. So this is a solver's line here. Okay, and you can see that this is decreasing with decrease in temperature. Okay, and this also means that the solid solubility, okay, of B in A is decreasing as you decrease the temperature, right? And you can clearly see here. So if I take a temperature, let me change the color. So suppose I take the temperature of say T1 here, okay, and then say T2 here. Okay, so T2 is less than T1. Okay, and the solid solubility of B at a temperature of T2 is less than the solid solubility of B at a temperature of T1. That is what it means. Okay, so if you have a phase diagram like this, or a part of the phase diagram like this on the say left side or say right side also, whatever. Okay, so then in that case you can form precipitates. Okay, that is the one of the basic criteria to to say whether a given system can form precipitates or not. Okay, so the solver's light should decrease with the temperature. Okay, now let's talk about how do you form precipitate. So this is the criteria, but what steps you need to take to form precipitates. Okay, so say here in the phase diagram we have A, say aluminum and copper, right? Then B is copper. So say A is aluminum and B is copper, and we are going to use this aluminum copper system to explain some of the phenomena in precipitation hardening in the subsequent lectures. Okay. Okay, so let's talk about the steps now. So you have 3 steps to form precipitates. The first step is called solution treatment. The second is called quenching. Okay? And the third is aging. Okay, so these are the 3 steps you have to follow to obtain precipitates in aluminum alloys. Okay, so if I draw a heat treatment cycle, it is going to look something like this. Say you have a temperature on the y-axis. Okay, then you have time on the x-axis. Okay, so for solution treatment, let's change the color. Okay, so it will be say something like this. Okay, then you are going to quench it to some temperature, then you're going to age it, something like this. Okay, so this is your cycle, heat treatment cycle. Okay, now so this the top one. So what you have to do, you have to take your sample, you have to go to high temperature, say in this case T0, and I will use this nomenclature T0, T1, T2 and use phase diagram and then explain it to you. Okay, so this process here we call it as solution treatment. Okay, so you're going to a temperature T1, T0, and then you're going to leave your sample for long time there at that particular temperature T0. Then you are going to quench it. So this second process here, so this process here is called quenching. Okay, so you are quenching it. To say a temperature of T1. Okay. Now after quenching, you are going to again take the sample and then heat it to a temperature which is much below the solution treatment temperature. Say here, this one, okay, to T2. And this process is called aging. And then you subsequently cool it down after you leave it there for some time. Okay. So this is the overall process. So we start with solution treatment, then we go to quenching, and then we age it. Okay, we call it aging, and thereby we are going to form precipitates in the given alloy system or given aluminum alloy. Okay, so now let's understand this with respect to phase diagram. Okay, and then I will also write the what we typically do in solution treatment, quenching and aging. Okay, so let's Okay, let's first write down and then we will use phase diagram to understand this concept. Okay, so solution treatment. Okay, so what we are going to do, we are heating the alloy okay, to a single phase region to dissolve any soluble precipitate. I will explain all this, okay? Just wait. So we are heating the alloy to a single phase region so that we can dissolve the precipitates. Okay. Now the next is quenching. Okay. So after solution treatment, we are going to cool the sample. Okay, very rapidly. Okay. So cooling very rapidly to room temperature or lower. Okay, so to room temperature or a slightly lower temperature so that we can obtain super saturated solid solution. Okay, and the last one is aging. So after you quench it, you have to age it. Okay, so here, so when we do solution treatment, I told you heating we are going to do at T0, right? I will use the phase diagram to explain this. Then cooling we are going to do a certain temperature which is say T1, and then aging again we are going to heat to a temperature of say T2 to form precipitates. Okay, in this case say T2 to form precipitates. Okay, so these are the 3 steps we have to follow to form precipitates in aluminum alloy. Okay, so now let's use phase diagram and try to understand it. Okay, okay, so let me draw. Something like this, right? So you have temperature here, and then we were talking about A and B previously. So you have weight percent of B here, and somewhere here you have beta, right? So this is going to be alpha plus beta, and this is your single phase region here, right? So if you see, this region is your single phase region, right? And that is what I meant when I wrote here, if you remember, heating the alloy to a single phase region. Okay, so we have to heat it to single phase region, which is shown here, just marked here, right? This region. Okay, so the first step is solution treatment. And what we are going to do, we are going to heat it to a single phase region, which is alpha here. Okay, so let's heat it to a temperature of T0 And okay, before that we have to choose some composition. So let's choose this particular composition here. Okay, having a concentration of C naught. Okay, and then we are heating it to a temperature of say T naught. Okay, which lies here in the single phase region. So you had a sample which contained two phase region, beta was also there, right? So what you are going to do, you are going to heat the sample to a temperature of T naught, and the composition of this alloy is this, right? So at that particular temperature and for this particular composition, you are going to obtain a single phase region which is alpha. Okay, and you have dissolved all the precipitates. That's what I wrote also before, right, for solution treatment. So if you talk about the microstructure, you're going to see a microstructure at a temperature T naught which will not have any precipitates. Okay, so if it is a polycrystalline material, you are going to have a microstructure like this. So this is your microstructure. Okay, where you can see the drain boundaries, and these are alpha, right? It's a single phase. There is no phase, other phase. There is no beta phase. We have dissolved all the precipitates in the alpha matrix to form a single phase alpha here, and that is the purpose of doing solution treatment. Okay, now the second, so this is your solution treatment, after solution treatment. So I can write this as after solution treatment. Okay, right? Now, since you have dissolved all the precipitates, the next step was to quench it, right? So you're going to quench to some temperature, say here T naught or T1, right? T1. Okay. So you have quenched it. So you are now, this is my composition line. Let me change the color. Okay? So this is your composition line. Okay. Now, ideally, if I am using this composition, right, you are at, and we are at temperature of say T1, you should form precipitates, right? Because this lies in two phase region, alpha plus beta, isn't it? But since we are quenching it, we are not allowing these solute atoms, B atoms, to go out. We have not given sufficient amount of time for these B atoms to go out from the matrix to form beta phase. Okay, so almost all the B atoms are going to stay in the matrix, and that's why we call it supersaturated solid solution. Okay, remember alpha is also a solid solution, right? So when we do solution heat treatment, solution treatment, we are going to form alpha, which is a solid solution. Now when we quench it, we are going to form supersaturated solid solution, which I also mentioned here. Okay, so all the B atoms are inside the matrix and it is supersaturated, and that supersaturation is given by this difference. Okay, now it is not in equilibrium condition, because equilibrium condition is, or phase, based on the phase diagram, I can say at equilibrium you are going to have alpha plus beta, isn't it? So B atoms would like to come out from the matrix. Okay, so let me draw the microstructure. So microstructure as such will remain same if we are in T1. Okay, so microstructure doesn't change much. You're going to observe the same microstructure. The only difference here would be that this is not going to be an equilibrium structure, and B atoms will try to come out from the matrix to form beta phase, because that is the equilibrium structure. So this microstructure is after quenching. Okay, now if I leave the sample at room temperature and give sufficient amount of time, like years, right? So what will happen? These B atoms will come out and they are going to form beta phase. Okay, but since we want to do everything faster, and if suppose we are working in industry, we cannot give years to form some precipitates, right? So what we do, we heat it to a slightly higher temperature, say T2. So what we are here, T2, let me draw T2 here. So this is your T2. Okay, so suppose we are heating to this particular temperature T2. So we heat the sample to a temperature T2, okay, and then we are giving some driving force, right? At higher temperature, these atoms then quickly come out and starts forming precipitates in the matrix, because the equilibrium structure suggests the microstructure should be having alpha plus beta. Okay, so when we heat it, what we are going to form is called precipitates. So these are your grain boundaries, what I'm drawing now. And then you start forming precipitates. It's something like this. All these are schematics, right? Okay, so this is the microstructure at T2 after, say, aging. Okay, and these blue ones, what I have drawn are precipitates. Okay, and the remaining matrix is obviously is going to be alpha, right? So here we also have alpha. So the microstructure here is alpha plus beta. Okay, alpha is a solid solution of B in A, right? And even after quenching, your microstructure is going to have only alpha, but it is supersaturated. Okay, and this after solution treatment, it is going to have only alpha. I told you already. Okay, so this is how we do agent treatment, right? So we start with solution treatment. We dissolve all the precipitates, prior precipitates, and we form a single phase, right? Alpha. So in this case, alpha, right? Single phase. So this region. Okay, this. Then we quench it and we form supersaturated solid solution, where given a chance, if you give sufficient driving force, B atoms will come out from the matrix and they will form precipitates, because the equilibrium diagram or phase diagram suggests the microstructure should be alpha plus beta, right? So what we do aging treatment. Okay, so we go to a sufficiently higher temperature, slightly higher temperature, and then we heat it there to form precipitates, okay, which is beta here in this particular phase diagram. Okay, now the aging treatment I mentioned right before, that you can, after quenching, you can leave it at room temperature and give sufficient amount of months and years, right? So, and when this happens and you form precipitates, the process is called natural aging. Okay, so naturally your material, your aluminum alloy is going to age, so we call it natural aging. You are not going to put your sample in the furnace, you are not going to apply external heat to it. Okay, so that is called natural aging. That means no external heat. It is going to happen, or formation of precipitates is going to happen naturally. But when we heat it in the furnace, we are applying some external heat. We call it artificial aging. That means we are supplying some external heat, okay, so that precipitates can come out from the matrix much faster. Okay, so applying, giving external heat. That means, say, heating in the furnace. Okay. Okay. So this is how we do agent treatment. Okay. And this is the process by which we form precipitates in the matrix. Now these precipitates are going to interact with dislocations. Also, these precipitates, are going to change its characteristic in terms of size and interfacial boundaries as we age it, or we give more time. Okay, so with respect to time, the nature of the boundary of precipitates and size, they change. So we will discuss that now.